I got a housekeeping note for those doing the bioretention field trip. The transportation is going to be at 1 p.m. at the back of the building, okay? Our next presentation is updated one-year coastal flood elevation as a threshold of coastal flooding. The presenter is Dr. Kaveh Zomorodi. He's a principal engineer and a senior hydrologist at the Dewberry Companies. He received a PhD in civil and environmental engineering, hydrology and water resources from Utah State University in 1988. He has over 34 years of work experience in academic and consulting engineering work, dealing with surface water, groundwater, and water resources planning and management. Dr. Zomorodi has published or presented over 60 technical papers in various journals and conference proceedings and numerous R&Ds and project reports. His work has led to the development of new simplified approaches to several flood hazards analysis problems, including frequency analysis of flood damage data and evaluation of average annual number of floods for evaluation of cost of flood mitigated projects. Dr. Zomorodi is the primary author of the computational procedures of the 2014 Federal Transit Administration HMCE tool and its coastal flooding recurrence interval estimator. Other technology developments by Dr. Zomorodi include new methodology and equations for estimating design peak discharges impacted by climate change, post-fire peak flows, groundwater mounding, modified sheet flow trouble time, and prediction of levee bridge geometry and probabilistic flood analysis.
Thank you, Roberto.
You're welcome.
Hello, everybody. I hope everybody is doing good so far. I am Kaveh Zomorodi. I'm with Dewberry Companies in Fairfax, Virginia. And today I'd like to tell you a little bit about my recent work on the updated one-year coastal flood elevation. Now, you may think that this is a resilient design session, and we should all be talking about extreme floods. Why are you taking us back to minor floodings, one-year flooding, and all that? And hopefully I'll be able to shed a little bit of light on that, the significance of the one-year flood and how it works out into the whole picture of resiliency. As a background, we all know that in many areas, sea level rise is causing more frequent and damaging nuisance and minor coastal flooding. Now, there are some common minor coastal flooding indexes such as the mean high water, high tide, flooding, king tide, etc. But none of those indexes really have any probability attached to them and really have very minimal use in terms of engineering design for us. On the other hand, if you talk about the one-year coastal flooding, which is, in my view, the water surface elevation that has an annual exceedance probability of 99%, that's the flooding elevation which you can really identify with a given probability of occurrence every year. Now, the one-year flooding is what I call the annual flood at coastal areas. And that should not be confused with the mean annual flood, which occurs every 2 years. One-year flooding is almost assured to occur every year. So it can serve as a threshold above which real flooding or damaging flooding can occur, especially floodings that cause roadway inundation and problems like that. Now, it has other significance because, for example, previous studies tried to tie the difference between the 50-year coastal flood and the 1-year coastal flood to how severe climate change will make the future conditions to be. For example, one study said that for more than 90% of their US sites, the difference between the 50-year and 1-year coastal flooding elevation was less than 1.64 feet. And that really sounds scary because that means that tomorrow's 1-year event, which you all started to discount as unimportant, will actually be tomorrow's 50-year event. So, in other words, the future 1-year event will be as big as what the 50-year event is today. So we better have an idea of what that 1-year flooding is. The other application of 1-year flooding is in benefit cost analysis of coastal flood hazard mitigation. FEMA benefit cost analysis tool actually used to require the input of 1-year coastal flood elevation. And everybody was asking, how are we going to get that? And the answer was, it's your responsibility. So they've actually changed. We actually worked with them with several benefit cost analysis module revisions, and that's one of the things that is no longer required as an input. But Dave's presentation, which was first presentation today, reminds me of the fact that BCA is a complex thing to do. And you were right, there is such a code that says currently BCA methodologies are not available to assess project effectiveness if you're updating your bridges or other transportation structures for climate change. That's true. But a few years ago, we tried to do something about that. We actually worked on an NCHRP to develop procedures to decide whether it would be cost effective to upgrade your transportation facility to be mitigated against future climate change. And I personally worked on a watered down, simplified BCA procedure that hopefully every engineer can use to make that decision. I don't know if Federal Highway actually has published that or is publishing it, but we applied it to a couple of pilot projects, and the results were reasonable. So there is a way to actually do that. The problem with it is that people, when they think about future conditions in terms of benefit cost analysis, try to apply the conditions that won't realize until, or won't materialize until 50 or 100 years from now into today's conditions. In other words, they want to spend today's dollars to prevent problems that is not fully realized until 50 or 100 years from now. So in the meantime, they'll be over-designing their bridge for the next 50 or 100 years. And that is a problem when we talk about benefit cost analysis in that terms. But that's a different story. Another application of 1-year coastal flood elevation is to use it as tailwater conditions of coastal flood hazard mitigation or outlets of your drainage system into open water. Now, a couple of background related studies. We worked under STAR 2 on developing improved high-frequency water levels to estimate impact on average annualized losses. So average annualized losses is another instance where a knowledge of 1-year coastal elevation would be very beneficial. And that study was followed by a presentation by my colleague, Jeff Gangai, along with Lauren Schmidt of FEMA. The title was Resolving the High-Frequency Coastal Flood Risk for Probabilistic Flood Analysis and Mitigation Action. So you can immediately see that it's not just the low-frequency flood that needs to be well-defined, understood, and accounted for, but also the high-frequency flood plays a role. And on the right, I'm showing a graph where the x-axis is annual exceedance probability, the y-axis is the water surface elevation in the coastal area. And generally what you have from a FEMA study is water surface elevations from 10% to 1%, in other words, 10-year and above. And then that lower segment is totally missing. The elevation points are missing. And that is a problem when we want to do applications such as calculating the mean annual flood loss. It may not sound very interesting or very dangerous, but that's actually what sets the flood insurance rates. If you don't have a good idea of the mean annual flood loss, then your flood rates are going to be just conservatively set that's very high. So why this study? We know that NOAA actually provides the water surface elevation 99% in many of their co-op coastal stations. The problem is that their values are limited only to the NOAA coastal station locations. Also, their values are sort of outdated. They belong to 2018, but not really. They are actually 2001 values that NOAA actually calculated the values for 2001, not just the 1 year, all of their coastal elevations. But then they added the sea level rise to all of the frequencies. The same amount of sea level rise was added to the 1 year that it was added to 100 years. And that's not very proper way of doing it. So in this study, what I have done, and I've gone back to recalculating the values of the coastal flood elevations for the 1 year, 10 year, 50 and 100 year for all of the NOVA stations, to bringing it up to the year 2021 using the SLR trends, which I apply to a non-stationary generalized extreme value statistical distribution, which, by the way, is the same distribution that NOAA has used to come up with their 2001 values. So at a couple of stations, I verified that I get the same values for the 2001 as NOAA did, and then I applied it to all other stations to update them to 2021. Now, the coastal flood studies and models commonly provide extreme floods, right? In many areas, whether you have FEMA firm or not, you may have an idea of the 100-year or 10-year water surface elevation. So this study investigates a relationship between the 1-year coastal elevation and those extreme flood elevations. And hopefully, if there is good regression between the two, good correlation, then we can find a way to estimate the 1-year coastal elevation for ungauged areas. So what is a 1-year flood elevation? Here's a example from a FEMA coastal station frequency analysis. On the x-axis, you have the return period. On the y-axis, you have the coastal elevation. And the 99%, the 99% annual exceedance is what we're talking about today. So FEMA has these charts on which they actually have the 99% flood elevation marked for 2018, which is really not 2018 completely, but anyway, their 2001 values are slightly lower, but they're more accurately calculated. So what is one-year coastal elevation? In many of these charts, you can see that the 1 year sits slightly above the mean high water. So many people understand mean high water, so they have to know that it's slightly above that. Now, previous studies, global tides and surge analysis, have found a very wide range of difference between 1 year coastal elevation and mean high water. They go as large as 9.2 feet, which I don't see that kind of difference in any of the NOAA stations for US. So sea level rise impacts not just very large floods, but it also impacts the 1 year coastal flood elevation. So that's why we have to account for sea level rise in the non-stationary extreme GEV distribution and come up with the updated values. Now, I did this for all 112 NOAA coastal stations. One thing to note is the meaning of the flood levels in this calculation is the same as the meaning of the extreme flood elevations that you can get from NOAA coastal stations. What it means is that these are really representative of storm surge, which are a combination of astronomical tide, storm surge, and limited wave setup caused by breaking water. They do not include wave runoff, which is the movement of water up a slope. But that's okay. This is what usually gets used in many design practices. Now, so the GEV parameters were available from, actually NOAA provided those to me, the values that belong to 2010. And I updated them from there on to 2021 for 3 different regions of NOAA coastal stations: Northern Pacific, Northern Atlantic, Tropical, and Gulf of Mexico stations. And the procedure, how I did it, is laid out here, but the end result gave me the 1 year, 10 year, and 100 year updated water surface elevations. And for updated values, a number of the stations, especially in isolated islands, did not really show good consistency with the other stations in the same area or same region. So those stations really dropped out of the analysis. Okay, so we had 112 station results. So this graph, on this graph, the blue curve shows the frequency distribution of the result for the difference between 50 minus 1 year. Remember that's the difference that I told you that the previous study showed a very wide range and made a scary prediction that the future 1 year would be as big as today's 50-year coastal flood elevation. Our results, at least for these 112 stations, don't really confirm that, because the distribution of the difference goes from very small value to no more than 6.6 or 6.7 feet. So if you look at the distribution of 10-year minus 1 year, that's more in the range of what they were saying, 1.6 or 1.67 feet. So we can probably say tomorrow's coastal 1-year flood elevation would be slightly bigger than today's 10-year flood elevation. It wouldn't be as big as 50-year water surface elevation. So here's the distribution of all of the 112 stations showing the relationship between the updated 100-year and the updated 1-year coastal elevation. You can see that there is generally an increasing trend, but there is a lot of scatter of points. So in order to hope for a good correlation between the two, I had to go into individual regions. So for Northern Pacific Station, using all of the 37 stations, I actually found a very good correlation. This equation has a very high R-square value and shows good correlation between the 1-year water surface elevation, 1%, which is 100-year water surface elevation, and the 99%, which is the 1-year coastal elevation, which the R-squared can actually improve if we get rid of one of the points, which is the Tokyo point in Washington State. But even with that, the correlation is good enough, allowing us to be anywhere in this region that's not even near any of the coastal stations, and being able to predict or get a good estimate of the 1-year coastal elevation only by knowing the 100-year coastal elevation. The results weren't as encouraging for the Northern Atlantic stations, using all 39 stations in that region. And the 100-year really didn't correlate very well, or the 1-year really didn't correlate very well with the 100-year. So I had to go down to the 10-year. And going down to 10-year water surface elevation instead of 100-year improved the correlation between the two. However, the correlation wasn't as good as the Northern Pacific. So in this area, anywhere, even away from any of the coastal points, coastal stations, you can get a good idea of the 1-year coastal flood elevation by knowing the 10-year flood elevation, which is available customarily from FEMA studies or other studies. The situation gets worse when you move to the tropical and Gulf of Mexico stations. Now, there are many islands involved, and the 1-year flood elevation didn't correlate very well with the 100-year or 10-year flood. You can develop a 2-parameter equation using both the 100 and 10-year to predict the 1-year, but then there is the statistical problem of interdependence between your predictive values, which I really didn't like. So I didn't even present any of those equations with there because they won't be statistically defendable. So instead of developing an equation for the entire region, I had to go down to smaller areas, subsets of the region. For example, for Hawaii stations, if you exclude one of the available stations, you can get this equation which predicts the 1-year water surface elevation based on the 100-year flood elevation. Simple linear correlation here because there's only four really valid points available. If you move down to East and South Florida shore stations, then you have to drop out more stations. So when you exclude a few of the stations in that region, you can get this good correlation, which of course is not going to be valid around the stations such as Fort Myers, because those stations drop out of the equation. But in other areas that are included, you can get an idea of the 1-year coastal elevation based on knowing the 10-year water surface elevation. So, in summary, relationship of the one-year coastal flood elevation updated, of course, for SLR to extreme floods that were also updated to the year 2021 was investigated using the data from all available NOAA coastal stations from 3 different regions. And the conclusion for each region was a little bit different. For Northern Pacific stations, using all stations, a strong correlation was found between the 1-year and 100-year water surface elevation. A regression equation was developed allowing reliable prediction of the 1-year water surface elevation anywhere in this region. I was talking with a California colleague of mine and mentioned the fact that the best results was obtained for their region. And surprisingly, he wasn't surprised. He said, yeah, we always knew that there is a good correlation between different flood elevations here. Your results are consistent with my expectations. Anyway, for the Northern Atlantic stations, the results weren't as strong, but relatively strong relationship between the 1-year and the 10-year water surface elevation was established that allows getting a good estimate of the 1-year flood elevation based on the 10-year, and for tropical region and Gulf of Mexico stations, no acceptable equation was obtained for the entire region. We had to go down to sub-regions, as I explained with a couple of examples for Hawaii and Eastern South Florida. With that, I'd like to thank you for your attention and open it up for any possible questions. But please speak up if you have.
Yeah, just a question. You're saying that some of your statistics doesn't work, but obviously, in Atlantic, you're dealing with northeastern storms, you're dealing with tropical and subtropical storms, so all those stations are actually involved in different, different conditions. So, put the statistics over all of that, such a wide area from Florida all the way to Boston.
You're right, but that wasn't my categorization. That's from NOAA regions. NOAA has put them together in that.
Yeah, but even if you do the FEMA studies, you have to consider different type of storms, and similar for the Gulf. So is there your future maybe research going towards to those delineation more on the group those stations more on the based on the type of the storms which those stations are exposed to?
That would be
hurricanes always have a different.
Yeah, it would be a good idea, but at this point I'm not planning to continue this, but that would be a good way to refine the results. Thank you. Thank you.